Right now, more than 3 billion miles from the sun, there is a small, frozen world with a sky that should not be doing much of anything. No oceans to drive weather. Sunlight so weak that noon there looks like deep dusk here. An atmosphere so thin that if you scooped up a cubic foot of it, you would be holding almost nothing at all. And yet that sky is running a temperature control system. When NASA's New Horizons spacecraft measured the upper layers of Pluto's atmosphere in 2015, the numbers came back wrong, not slightly wrong. About 30 degrees Kelvin colder than the leading models predicted, which is roughly 54 degrees Fahrenheit off target. On a world where every degree is hard-won, that gap was enormous. One scientist had an explanation. His colleagues thought it was a stretch. He himself called it a crazy idea, and there was no instrument on Earth or in orbit sensitive enough to test it. 8 years later, one was. So here is what we are going to answer. What is actually making Pluto's sky colder than physics said it should be? Why did a telescope built to study the first galaxies end up settling an argument about a dwarf planet? And why does a frozen world quietly bleeding heat into space have anything at all to say about how life got started here? You're watching Beyond the Signal, where we follow the evidence to the edge of what science knows. If you like discoveries that come with a paper trail instead of a panic headline, subscribing helps more of these reach people who want the same thing. Let's go back to when Pluto was nothing but a dot. In 1930, at Lowell Observatory in Flagstaff, Arizona, a 24-year-old farm kid from Kansas named Clyde Tombaugh sat in front of a machine called a blink comparator. His job was to load 2 photographic plates of the same patch of sky, taken nights apart, and flip between them. Stars stayed put. Anything that jumped was worth a second look. It was slow, cold, repetitive work, and for months it produced nothing. Then one afternoon in February, a speck jumped. That speck became the 9th planet, and for the next 76 years it stayed one. Then in 2006, the International Astronomical Union adopted a new definition of the word planet, and Pluto did not meet all 3 conditions. It became a dwarf planet. People were genuinely upset. School posters were suddenly out of date. But here is the part most retellings skip. The demotion had nothing to do with what Pluto was like. It was a bookkeeping decision about categories. And in 2006, we still barely knew anything about the object itself. Put that in perspective. Even with the best telescopes available, Pluto was a smear of light a few pixels across. We could not map its surface. We could not resolve its shape. Estimates of its size shifted around for decades. Almost everything written about Pluto in the 20th century was inference, stacked on inference. We now know it is about 1,477 miles across, roughly 2/3 the width of our own moon. It circles the sun on a long, tilted oval orbit that takes 248 years to complete, averaging about 39 times farther out than Earth. Sunlight that far away is a fraction of a percent of what falls on your driveway, and the cold is close to unimaginable. The average surface temperature sits near 387 degrees below 0 Fahrenheit. At those temperatures, nitrogen, the gas making up most of the air you are breathing right now, is not a gas. It lies on the ground as ice, and in places, it flows like a glacier. So nobody was surprised that Pluto was cold. Cold was expected. The surprise came from a much thinner, much higher layer of Pluto, and it came from a spacecraft that got exactly one chance to look. New Horizons launched in January 2006, 7 months before the vote that reclassified its target. It crossed the solar system for 9.5 years. On the 14th of July 2015, it swept past Pluto at roughly 30,800 miles per hour, at a closest approach of about 7,800 miles above the surface. There was no braking, no orbit, no second pass. The entire encounter that mattered lasted minutes, and the spacecraft was so far away that a radio signal needed about 4.5 hours just to reach Earth one way. By the time controllers in Maryland saw confirmation that the flyby had worked, it had already been over for hours. What came back rewrote the world. There was a vast, pale basin shaped like a heart, now called Sputnik Planitia, filled with nitrogen ice and almost completely free of impact craters. A crater-free surface on a 4-5 billion-year-old body means one thing. Something has been resurfacing it recently. There were mountains of water ice rising as high as 11,000 feet. At Pluto's temperatures, water ice is not slick or soft. It behaves like bedrock. It is the load-bearing stone of that world. And then there was the sky. As New Horizons looked back at Pluto with the sun behind it, the cameras caught something almost delicate. Layer after layer of haze, glowing blue, stacked in roughly 20 distinct bands and extending more than 120 miles above the surface. A dwarf planet at the edge of the planetary system had a structured, layered atmosphere. That was beautiful. The data that came with it was a problem. An instrument aboard the spacecraft called Alice watched sunlight pass through Pluto's atmosphere as the spacecraft slipped behind it, a technique called a solar occultation. When light filters through a gas, the gas absorbs specific colors, and those missing colors tell you what is there and how hot it is. The reading came back near 70 Kelvin in the upper atmosphere. Models had expected something closer to 100. Something was pulling heat out of Pluto's sky, and nobody could say what. Here's the part most headlines miss. The standard assumption about haze is that it warms things. Haze absorbs sunlight, and thick, hazy atmospheres tend to trap energy. Titan, Saturn's largest moon, has an orange hydrocarbon haze that works roughly that way. Pluto's haze forms the same basic way, through sunlight breaking apart methane and nitrogen high in the atmosphere, with the fragments recombining into larger organic particles that drift downward. In 2017, Shi Zhang, a planetary scientist at UC Santa Cruz, published a paper in Nature proposing the opposite. He argued that on Pluto, the haze particles absorb the little sunlight available, warm up as solid grains, and then radiate that energy straight back out as mid-infrared light far more efficiently than the thin gas around them ever could. In that picture, the haze is not a blanket, it is a radiator. And because the haze particles, not the gas molecules, would be running the energy budget, Pluto's atmosphere would be unlike any other atmosphere we had studied. Zhang has been candid about the reception. He has described it as a crazy idea and said many of his peers were skeptical. But he did something that separates a hypothesis from a guess. He made a prediction that could fail. If the haze was doing the cooling, then those particles had to be glowing in the mid-infrared. Point a sensitive enough telescope at Pluto, and you would see that glow. If it was not there, the idea was dead. In 2017, no such telescope existed. On the 25th of December, 2021, NASA launched the James Webb Space Telescope. Webb does not primarily take pretty pictures. It splits incoming light into a spectrum and reads it, and its mid-infrared instrument covers exactly the wavelength range where Zhang's predicted glow should appear. There was still one obstacle. Pluto and its largest moon Charon orbit so close together and sit so far away that earlier instruments could not separate their heat signals. Every previous thermal measurement of the system was really a blend of two objects, and a blend can be explained several different ways. It is like trying to judge one voice in a room where two people are talking at once. Webb could pull them apart. In 2022, it measured separate thermal light curves for Pluto and Charon across roughly 15 to 25 micrometers. And in May 2023, it captured a high-quality, mid-infrared spectrum of Pluto and its atmosphere across a range no instrument had ever covered. The results were published in Nature Astronomy on the 2nd of June 2025 by a team led by Tanguy Bertrand of the Paris Observatory, with Zhang among the co-authors. They detected the thermal emission of Pluto's haze directly. The measured fluxes indicate the haze is made of titangent-like organic particles mixed with hydrocarbon and nitrile ices. And the conclusion in the paper is that the haze largely controls the energy balance of Pluto's atmosphere. Think about what that means. Pluto is not merely cold because it is far from the sunday. A layer of soot-like organic particles suspended in its sky is governing how much heat that sky can hold, which means the haze is shaping Pluto's temperature structure, its climate, and its atmospheric circulation across seasons that each last decades. The authors are careful, and so should we be. This is strong observational evidence for a mechanism, not a closed case. But it is a prediction made in 2017 and matched by data collected years later, which is about as clean as planetary science gets. And it does not stop at Pluto. Neptune's moon Triton and Saturn's moon Titan both have nitrogen and hydrocarbon atmospheres full of haze. If particles can run the energy budget on one of them, the models for the others need another look. Now, that same haze had already left evidence somewhere else. Not on Pluto, on the moon next door. Pluto has been slowly losing its atmosphere for billions of years. Gas drifts up, escapes Pluto's weak gravity, and leaves. That much was expected. The question was where it goes. Charon is about half Pluto's diameter and orbits roughly 12,000 miles away, close enough that the two are tidally locked, each permanently showing the other the same face. When New Horizons imaged Charon, most of it looked like what you would expect: gray, cratered water ice. Except at the North Pole, where there is a large, dark, distinctly reddish-brown cap. Mission scientists nicknamed it Mordor Macula. In 2016, a team led by Will Grundy published an explanation in Nature. Because of the geometry of Charon's spin and orbit, each pole sits in unbroken winter darkness for around a century at a time. That makes the pole an extraordinarily effective cold trap. Methane escaping from Pluto drifts across, freezes onto that frozen pole, and accumulates. When sunlight finally returns, The frozen methane does not simply boil away. Ultraviolet light and charged particles break the molecules apart, and the fragments reassemble into heavier reddish organic compounds called tholins. Those heavier compounds are not volatile. They stay. Every cycle, the stain gets a little deeper. Two worlds, one losing pieces of its sky, the other catching them and turning them into pigment. And the same JWST campaign that measured Pluto's haze also tracked material moving from Pluto's atmosphere onto Charon's poles, an interaction researchers on the team describe as happening nowhere else in the solar system. Charon had one more surprise. In October 2024, a team led by Silvia Protopapa of Southwest Research Institute published results in Nature Communications from Webb's near-infrared spectrograph, covering wavelengths New Horizons could not reach. Alongside crystalline water, ice, and ammonia compounds, they detected carbon dioxide and hydrogen peroxide. The carbon dioxide most likely comes from reservoirs buried since Charon formed, excavated by ancient impacts. The hydrogen peroxide is a signature of processing, water ice being broken and rearranged over time by ultraviolet light and energetic particles. A moon that looked chemically boring turned out to be layered and actively worked on. So keep score. Pluto's sky governs its own heat. That sky leaks onto its moon and colors it, and underneath all of it, the surface itself has been raising questions since 2015. In the region named Tartarus Dorsa, New Horizons photographed rows of aligned ridges made of methane ice, spaced several miles apart, with relief on the order of 1,000 feet. The closest thing on Earth is a formation called penitentes, spikes of ice carved by sunlight in high, dry mountain deserts. Ours reach a few feet. Pluto's are hundreds of times larger, sculpted by ice turning directly to vapor over many climate cycles. New Horizons only imaged one hemisphere at high resolution. In July 2025, a team led by Ishan Mishra at NASA's Jet Propulsion Laboratory published an analysis in the Journal of Geophysical Research, planets that worked around that limit. Instead of images, they used photometry, measuring how brightness changes with viewing angle to infer how rough a surface is below the resolution of the camera. The poorly imaged, methane-rich regions came back as the roughest terrain on Pluto, more than twice as rough as the known blade fields. Their interpretation is that Tartarus Dorsa is the western edge of a belt of bladed terrain, wrapping more than 220 degrees of longitude around Pluto's equator. Not a curiosity. Possibly the dominant landform on the entire world. Then there are the mountains that should not be there. Wright Mons is about 90 miles wide and roughly 2.5 miles high. Picard Mons is larger still, around 140 miles wide and close to 4 miles tall. Both have deep central depressions and lumpy flanks that look like flows. On Earth, those shapes mean volcanoes. On Pluto, there is no molten rock available. In 2022, a team led by Kelsey Singer at Southwest Research Institute argued in Nature Communications that this region is best explained as cryovolcanic, built by repeated eruptions of a cold slurry of water ice from below sometime within the last 1 to 2 billion years. Which raises the question underneath everything else. If material was pushed up through miles of frozen shell, what was keeping it liquid? The leading answer is that Pluto has an ocean, not on the surface. Beneath it, under an ice shell that models put on the order of 100 miles thick, kept from freezing by heat still leaking out of Pluto's rocky interior. There is no photograph of it, and there will not be one. The case is built from geometry. In 2016, analyses led by Francis Nimmo and by William McKinnon showed that Sputnik Planitia sits almost exactly on the axis facing Charon, which is where extra mass would end up if Pluto slowly reoriented itself. Getting a positive mass anomaly under a giant basin is much easier if dense water beneath the shell welled upward to compensate. Add the network of extensional cracks across the surface, consistent with a shell that expanded as an ocean partially froze, and you have a coherent picture built from independent clues. It remains an inference. A strong one, but an inference. And if it is right, it describes something genuinely strange. A body of liquid water sealed in total darkness for billions of years, under crushing pressure, with no sunlight reaching it, ever. Here is the detail that ties this back to us. Those haze particles that control Pluto's climate do not stay aloft forever. They settle. For roughly 4 billion years, Pluto has been receiving a slow, continuous snowfall of complex organic material manufactured in its own sky. Similar chemistry, in a nitrogen-rich atmosphere without oxygen, is one of the leading pictures of what the early Earth looked like before life took hold. Xi Zhang has made that connection explicitly. Before oxygen built up in our atmosphere around 2.4 billion years ago, Earth's air was mostly nitrogen with active hydrocarbon chemistry. Studying how haze behaves on Pluto is one of the few ways to watch that kind of chemistry run at full scale. That is not a claim about life on Pluto. Nobody is making one. It is far too cold. What Pluto offers is something less dramatic and more useful. A working laboratory where prebiotic chemistry has been operating continuously, without interruption, since before Earth had continents. Meanwhile, the spacecraft that started all of this is still out there. In June 2026, New Horizons woke from its longest hibernation yet, 321 days, and reported back healthy from about 5.9 billion miles away. That signal took roughly 8 hours and 52 minutes to arrive. It is still measuring plasma, energetic particles, and dust in the outer heliosphere, and its funding has been argued over in Washington more than once. It will never see Pluto again. Nothing else is on the way. So here is where the evidence leaves us. Pluto's atmosphere is governed by suspended organic particles rather than by gas, which appears to make it unlike any other atmosphere we have measured. That was predicted in 2017, doubted, and then matched by JWST data published in 2025. Pluto is losing pieces of that atmosphere to Charon, and we can see the residue stained into Charon's poles. The surface is probably wrapped in a belt of methane ice blades, and it carries structures best explained as ice volcanoes. What we do not know matters just as much. We have not directly observed the ocean. We do not know whether it is liquid today or a slush slowly locking up. We do not know how many other Kuiper Belt objects run the same kind of haze-controlled climate because we have never had a close look at any of them. The world that got voted out of the club in 2006 turned out to be one of the most chemically active places we have visited. It was never the dead end, it was the door. Tell me which piece of this changed how you think about the outer solar system, the self-cooling sky, or the ocean nobody has seen. And if you want the case for a hidden ocean we actually have measurements for, the video on Europa is linked below. This is Beyond the Signal. Keep looking past the obvious.